Hi, I'm Nick. I'm the CTO of KissHub. I want to talk about how we moved to Kubernetes, why we did it, what the benefits were, what the potential challenges were, and I'll describe a bit in sort of detail about the steps we did to do that. And I'll finish off with a chat about, the sort of Kubernetes ecosystem. So the subheading of this is how we saved 80 grand a year and fully automated our DevOps, and that's basically about right. In fact, we probably saved a bit more than that. So KissHub, what is KissHub? KissHub is a crop intelligence and supply chain management platform for agriculture. So essentially, we connect a very disconnected supply chain. Agri-tech is pretty old school. You know, it's Excel spreadsheets, it's bits of paper if you're really unlucky, and it's very disconnected. People all the way in the supply chain don't really know what else is happening in the supply chain. So our mission is to connect this supply chain and to use that to provide insights, to enable enterprises to manage risk, to reduce costs, and to maintain and increase quality. We provide this as a web dashboard and a mobile application. The web dashboard is our main product, and this is what our enterprises use. We mainly focus on enterprises because they have cash to spend, farmers don't, and I want to use this to derive insights and to optimize their supply chain. We have a mobile application that effectively is mostly used to collect data from the farmers. So in order to do this, we have to collect a lot of data. We pull in a lot of data from various bits. So we pull in data from satellites, from weather data. We have our own network of weather stations for hyperlocal weather data. And we collect data from crop monitoring. So we use our mobile app is primarily about collecting crop monitoring data. So what stage are my potatoes at? We integrate with farm management systems and with load management systems. So there's a lot of moving parts. A lot of data going into the system, into this platform, and then coming out again. KissHub's been going for nearly 5 years now, and in common with lots of startups, it's been the development system was organic, shall we say, over time. Quite unusually for pretty much any of my startups, this one had 3 different cloud providers. It was actually split. They started off on Linode, then they moved some stuff to Amazon, then they moved some stuff to Google. So when I joined about a year and a half ago, I had the system which was spread over 3 cloud platforms based on virtual machines, just virtual machines. So it was a microservice-based system. So you've got your weather microservice, which is a RESTful API, great. Same with the satellite, similar for the web app itself. So great, microservices. But each of a clustered load balance microservice, but each of those were in their own virtual machine because it's the easiest way to do it, let's face it. If you want to deploy some stuff and you're not quite sure what the resource requirements are, the easiest, safest way to do it is I'm going to give a virtual machine to each of my replicas for each of my microservices. Great, that works. The deploy system was involved as a single Jenkins deploy server. And that deploy server, when told to deploy stuff on demand, it went away and pulled in a bunch of static assets and actually poked each individual virtual machine in turn to say, please Git pull the latest copy of the code. So effectively, Git was used as the deploy mechanism on each node. Again, sort of works, but there's lots of scripts floating around. So this Jenkins server has various deploy scripts written in Python and Fabric. There's deploy scripts on the nodes themselves in order to be able to do stuff. That all kind of works, but it's got problems. What's wrong with it? Biggest one, and this is coming as a thrifty Yorkshireman, is it's very inefficient use of resources. It's bloody expensive. You know, if you look at what the resource you're actually using in startup, and I tend to work in startups, you're usually generally using a lot less resources than you think you're using. Your CPU load would probably be negligible if you look at it en masse. There's memory load, again, if you look at it, you think, well, I'm not using that much. So when you start to work out what you actually need to deploy your system, it's usually a lot less than you think it is, certainly in startups. When you scale up, it may be different, but in startups, almost always less than you think it is. So going with a VM per microservice is pretty inefficient in terms of resources. This particular system is inconsistent because if I'm having my Git repository on each node, there's nothing to stop different nodes running different parts of the software. In particular, when a virtual machine restarted for any reason, so for example, if it ran out of RAM, scripts on there would say, oh, I've restarted, I need to call home to my Jenkins server to tell it to give me the latest copy of the code. It would go away and rebuild the static assets, push them to the bucket, and then tell the virtual machine, git pull your latest copy of the code. Which of course means that if you restart a machine, it could be on a different version of the software. Worst comes to worst, you could have lots of machines on different versions of the software. And because it's upgrading in place, if you don't detect that the code you're about to deploy is actually going to work and it's not going to blow up in flames, just the act of deploying something could break your system. And if you're under heavy load, when you deploy to a particular node, that's effectively taking that node out of circulation. So your load has now increased because now you've got fewer nodes. So you could end up with a catastrophic situation where everything just goes boom. That did happen, actually, at one point. It's slow to scale. You can make it scale again, but because this particular system where it's calling home to Jenkins server, doing stuff, calling out again, it's slow to scale. And it's opaque and difficult to maintain. There's just lots of scripts floating around the place. It's very imperative. You could make all this work. If you spent enough time, you could make this work using Git as a Git deploy mechanism. You could spend time and effort making it work with that. It's not, it's doable. But I have a shopping list. This is what I really want to do. I work in startups. I really don't want to spend time on DevOps. No one pays me for DevOps. We get paid for systems that solve customers' problems. So you want to build the best system that does as much as you can, automates as much as you can, is bomb-proof, and then gets out of the way. And lets the business build stuff that people actually want to buy. So what I really want is a system that can package my code so it can be deployed anywhere. I want to ensure I can only deploy working code. I never want a broken build. If it's deployed and it runs the servers, I want to make sure it's got to work every time. I want to easily be able to revert to a previous system, and I want that to be quick. I want to fully describe my deployed system, which means that I really want to know what's out there exactly. I want to know exactly what I've got in my servers. If someone drives a truck through my entire data center, I want to be able to recreate my entire system from scratch. Obviously not databases, because I'm assuming I'm still using a managed database. If someone drives a truck through your database and destroys the backups, well, then you're screwed. But for everything else, I want to know what it is, where it is, and be able to reproduce it and say, that's what my system looks like. I really want to be able to run the same system locally that I do remotely. If it's running on the servers, I should be able to run it locally. I should be able to run KissHub in a box. If I have 5 microservices, I want to be able to run all my 5 microservices here. The data might not be the same. I could probably make up my data, but I want to be able to run the same code here. I want to pack as much software on the silicon as possible. Now, obviously with the caveat, it's got to work, it's got to be resilient, it's got to be performant, but I want to make the most use of my resources. It's burn rate. The more I spend on my silicon, the less I can spend on developers. And I want it to automatically scale with usage. So if I happen something if I have the nice problem to have is I have lots of people using my system, so my load goes up. Great, I want my system to scale. I don't want to scale without me scaling it. It just scales. And it goes the other way around, and it shrinks. And this should all be opaque and transparent. So that's a heck of a shopping list. That's a lot. Yeah, I could code that myself, but luckily, someone's done it for me. So Kubernetes plus Docker pretty much solves all those problems for me. I've got to put a bit of effort in to get it up and running, but once it's up and running, it just runs. So a bit of background on Kubernetes and Docker. Actually, before I go, has anyone who in here has used Docker? Give a show of hands. That's pretty good. Who in here has used Kubernetes? That's about what I expected. Yeah. Okay, cool. So most people know what Docker is, but I'm still going to talk about it because some people haven't. What is a Docker? Docker is an implementation of a lightweight container. What is a lightweight container? I think this was lifted from the Docker website, but it's so good I had to display it. So it's a standard unit of software that packages up code and its dependencies so the application runs quickly and reliably from one computing environment to another. it's sort of like a VM. It's not quite. You can think of it like a VM. It's a good shorthand, but it's not. The reason it isn't is actually it runs on the native code. It's more like a fenced thing. You live in your application runs on a field, but it's fenced. It can't talk outside its fence unless you let it, and it can't do anything until you poke holes in its fence. But it's actually running on the same field as other things. So it's a lightweight container. It's not a VM. Because it's lightweight, it runs on native hardware, it's very quick. So performance isn't really an issue. A Docker container image, well, is a lightweight standalone executable package of a container. So it's basically Docker is simply an instance of a container. There are apparently other Docker things out there like Docker, but I think basically Docker's one, so it's not really worth worrying about them. What's Kubernetes? So Docker on its own is great. I've got my nice standalone package, and I'll talk a bit later about what do I do to build the thing and run it. But on its own, I've got now my standalone container. How do I run my container? And in a excuse me, in a noddy test tutorial, you've just got one Docker image which I can run. Great. But any non-trivial deployment has multiple. You've got a load balance set of these ones and these ones and these ones, and these expose these ports and these expose these ports, and they go to that load balancer. So a non-trivial setup has a whole plethora of Docker images floating about the place. So how do I get them working together? How do I deploy them? How do I get them talking to each other? Well, that's where Kubernetes comes in. So it's a system for automating deployment, scaling, and management of containerized applications, otherwise known as an orchestrator. So Docker images are your instruments in the orchestra. Your Kubernetes is your conductor. And your roadie, actually. But, let's say conductor. So what is Kubernetes? Well, one of the things I like about it is it's declarative. It describes what it wants the system to look like in data, in YAML or JSON. So I define what I want my system to look like. Kubernetes makes it so. Because Kubernetes knows what the world should look like, if anything goes wrong, it says, oh, okay, that's what it should look like. I'll make that so. If you go into Kubernetes and kill a node, kill a pod, and the pod is the kind of unit of deployment of Kubernetes, Kubernetes will go away and fix it. And it doesn't need your input. It knows what its view of the world is. It goes away and sorts it out. It's got built-in support for all the kind of DevOps fun stuff you want. So it's got built-in support for rollouts and rollbacks. The rollout's the most interesting thing, which obviously we use all the time. I've actually never had to use a rollback. I've tested it, it works, it was instant, but I've never needed it. And the reason I don't need it is because it's got built-in support for, the rollout support has built-in support for determining whether an app runs or not. So it's not going to deploy code if it doesn't pass your test. So our apps have our web apps have a URL which if I call and it passes and returns a 200, I know the thing's okay. Kubernetes won't let your new code get into its little cluster unless actually it passes that test. So I've never managed to deploy any code that breaks. So I've never had to roll back. I can if I want. It's nice to know it's there. I can if I want. I've never had to. But it automates that. It automates that testing to say, is this live? That liveness testing. For the Yorkshireman in me, again, bin packing. What that's saying is, tell me how much CPU do you think you're going to use? How much RAM? Okay, well, I know how much CPU and RAM you've got available. Let me sort it out. I'll shove that there, put that over there. I'll do that for you. If you do it, you can do that naively. You can just say, right, yeah, all right, you sort it out completely. You can actually, of course, give it rules and hints to say, please do this there and that there. So, for example, if you have a particular service which needs a lot of RAM, you can set up a node pool which is lots of RAM, and you say, okay, please prefer this in place of this one. So you can give it some hints. But if you're not worried about it, you can just say, just deploy it, sort it out for me. It's got built-in support for all the stuff you'd expect. It's got built-in support for load balancing, horizontal scaling, self-healing, as I said, error detection, etc. So Kubernetes is great. So I'm going to talk now about the steps we moved. We said that's why we moved, because I wanted to sort out my idiosyncratic deploy system into something I could maintain and basically not have to touch, ideally. And so I'm going to go through some at a high level the steps that were involved in moving to Kubernetes. So for a start, here's what KissHub architecture looks like. As I said, we collect data from various bits and pieces. So we've got weather data, satellite data, that feeds into some microservices called Kiss and Met and Kiss and Sat. Kissan basically means farmer in Hindi, by the way. And KissHub, which is the main API server. The managed databases stay as managed databases, unless they're QA. So we actually have a QA cluster and a production cluster. The QA cluster, there's no point paying for a managed database. You've got no resilience requirement. So for QA, our entire QA cluster is entirely in Kubernetes. I don't care if it's nuked tomorrow, we can recreate it. It's just QA. Production, obviously your data is pretty important. So your production database, we use managed databases, which is Cloud SQL, MLab for the MongoDB components. So how do we move this into Kubernetes from our 3 different cloud providers? So I'm going to go straight to the diagram. At a high level, that's what we're doing. I'll just concentrate on the QA cluster, for example. What we do is first, we're writing, and I'll talk a bit more about the detailed steps afterwards, but high level. Write code. So I've written my code, and I want my CI/CD system to work. So when I'm happy with it, it's gone through code review or whatever other processes you have in place. I push it to a particular branch. I will then run my entire test suite in whatever CI/CD system I want to use. In this case, it's Bitbucket pipelines. Tests pass. Hallelujah. No? Okay, we don't go any further. But let's say the tests pass. My next step, well, I've got working code now, so I can create my Docker image. We actually use Google Cloud Build for this because pipelines is bloody expensive and Cloud Build is really cheap. So we use Google Cloud Build to actually build the Docker image. Docker build. When that's done, it tags the image, pushes it to the Docker repository. What we then do is update our Kubernetes config. And I'll come to the config in a second. But essentially, the only thing you tend to change with the Kubernetes config is the actual name of your images that you've changed. It's bad practice. You can say :latest, and so it says always pick up the latest version of the code. It's bad practice because that means it's not declarative. It means that you don't have a definitive description of what your system is. If it should be an actual definitive tag of a released image, because then you know exactly what you've deployed. It's that. It's not happens to be the latest. It's that. We then, for completeness, we could commit this change config to Git, so we know exactly where it is. We then apply our new Kubernetes config, so we just tell Kubernetes to do it, to apply it. And as an extra step, we wait for it to finish, and then I tell someone on Slack it's deployed. None of this requires human intervention. The only bit we need that is for the human is to actually Git push to the QA branch. Everything else is fully automated. So, a bit more detail. How do I build my Docker image? This is the fiddly bit. It's actually a bit annoying. And I'm sure we can come up with a better language than Docker files because that's awful. It really is. But it's sort of, you're constructing, you only write, on the plus side, you only write this once. But what you're doing is, what are the steps I need to do to build my base image? So generally, every step up until the point of adding my source code into the image is your base image. Docker files can inherit from other Docker files, which is kind of a nice feature. So in this case, I'm inheriting from the standard Python 3.7 build. Great. If I had no other dependencies whatsoever, that's all I'd need to do. I just use the standard Docker image and I'm away. Well, once I had my source code. Generally, unless you've got a really trivial app, you need a bit more than that. This is a cut down. So I ripped a whole bunch of stuff out. But I left the GDAL stuff, for example. We rely on a particular library for some GIS work we do. GDAL has an idiosyncratic build system. It doesn't always work the way you'd expect it to do. So the easiest thing to do is just build from source. So we build from source. And that's what that bit in the middle is there. And so you're building up layer by layer your Docker file, and that's actually how Docker works. It's building layers on top of layers of file systems. The reason you get a lot of cruft in Docker files is because each layer still takes space. Even if you overwrite into the next layer, the first layer is still there in your Docker image, it's just not exposed. So you can end up with a lot of stuff that just takes up space. But, as we learned, don't get obsessed about that. I mean, you're deploying to a system which has got 10,000, 10,000 base T. It's ridiculously fast Ethernet wherever you're deploying to. And storage is dirt cheap. And the amount of time you spend trying to produce the absolute tiniest file is just not worth the outlay. Especially if you go for some of the really small images that are based on Alpine, which can give you random seg faults. So, if in doubt, stick with Ubuntu. You know it works. So it's slow and annoying, but you generally only have to do it once. Kubernetes. So how do I describe how my system looks like? So here's an example of the config. And if you look at it, and I've actually only got a snapshot here, but if you see, effectively, there's my app. It's called this. I have 2 replicas. The way I want it to update is a rolling update. And this is where this deploy goodness comes in. So what I'm saying is, right, when I'm deploying, I want you to add 2 new nodes, new pods, deploy to these pods. When they're happy and working, take the other ones down. Any one time, I want maximum 2 unavailable. So those are that's the only number of unavailable pods I'm allowed. So if you want to have no downtime at all, this is QA, so I didn't really mind, but I'd set that to 0. Fine. There must always be my full complement of replicas there, always. Creates new nodes, deploys to them, shuts the old ones down. So it's a roll and deploy. There are different variants. You can do one which just says deploy, change the whole world at once. Generally, even for a QA system, you want some continuity, so we don't tend to do that. You see there, that's the image. So that's my image I've built with my previous build system. Notice the big old SHA, which is the tag. Some indication of how do I build it. And the fun thing is, I want this much CPU and that much memory. So the first bit, the requests, tells Kubernetes how to bin pack. So, okay, I've got this much CPU. Okay, that can go there. But you can burst to this much. And then down off screen, you can't see these are the ports we exposed. Without that, it can't talk to the outside world, so it's pretty useless. So, okay, I expose this port, and only this port. We actually do this with templates. So we use Ginger 2 templates, mainly just so we can change that image thing there, and because we have a bit of legacy deployment where we have a tenants client architecture. These days, actually, Customize.io is built into Kubernetes, and you probably wouldn't use Ginger 2 now. If I did it again, if I ever revisit this, I won't use Ginger 2. How do I actually deploy this thing? Here's literally one-liner. If I have my config in one file, that's all I'm doing. Kubernetes, apply that file, please. Go off and do it. We only wait for it to finish because I want to notify someone on Slack that something's deployed. And in fact, that's what that looks like there. So in Cloud Build, when I've done all my stuff and I've done kubectl apply and I wait for it with another kubectl command, right, it's all done. Then I send a message to Slack saying this is deployed. And that was deployed, and there's the link, and there's a snippet from the Jira ticket associated with it. The notification stuff really works well with Slack. So if I've got certainly from QA, if I've got the reporter, if it's a bug, someone says I raised this bug, well, they're going to get notified when this fix is actually out there. They can go and verify it's fixed. Yep, it's fixed, Nick. Okay, we'll merge the master when it goes live. So that's just inspiration. So we have now automated our entire deploy system. We've saved a lot of cash in the process because we've gone from this 1 VM per microservice to fitting lots of services on the same node with no loss of service, with no loss of performance. In fact, actually, we've not done any tweaking at all. So where we specify that CPU and RAM, we could probably shrink that down a lot more if we spent some time on it. We've not worried about it at the moment, but there's savings to be had. But more importantly, we now have a consistent system which I can run locally. I can use Docker Compose, and I can build this locally. And I run on one platform, and I can describe it in a declarative way. And I spend no time on DevOps. And that's the most important thing, is that we just don't spend time on DevOps. We spend time building the product. We wrote our own Kubernetes config. You always have to roll your own Docker file. You can't get away with that if you've got a non-trivial setup. We also wrote our own Docker kubectl, Kubernetes config, and the machinery that pokes it off to Slack, etc. Mainly because there's nothing else quite there that does it. There's lots of systems that sort of do half of it. You've probably heard of Helm. They market themselves as the package manager for Kubernetes, and it kind of is. You know, if you want to get, say, something fairly simple up and running that's a well-known system, yeah, Helm will do that. Helm will deploy stuff in one line. But under the hood, it's this thing called Helm charts, which is yet another level of indirection on top of an existing config file. So if you want to deploy your own stuff, well, I think Helm charts, I'm not sure what it gains you at the moment. You have to write yet more config. Kubernetes isn't that complicated, really. It's got some weird idiosyncrasies to do with this match label stuff, but most of it's pretty standard. Here's this Docker image. I want these number of replicas. That's my RAM. That's my CPU. Please do it. So I'd probably, if I was doing this again, I probably would still roll my own until these start to mature. But they're getting better all the time. I mean, Jenkins X, Scaffold, and Argo are the ones that spring to mind that are built on top of this. The advantage of having a declarative system like Kubernetes, because it's built on data under the hood, you have options to do this. It's like electric cars, you know. It doesn't have to be. It could still be a coal station at the other end, but at least you now have the option to move it to, you know, recyclables. You've got the option if you design your system as data, you have the option to layer something on top. And so some of these may well fit your use case, in which case, you know, hey, go for it. But if you want to roll your own, it's not too hard. And in fact, there was a third-party system called Customize.io, which was all about doing small tweaks to Kubernetes config. That's now part of Kubernetes. So actually, there's a lot to be said for still owning your own stuff and doing it yourself. And yeah, and that's it. Here ends my talk.